Okay, so in today's lesson, we will focus on how to recognize trends in data sets and strategies that can be used to determine an appropriate mathematical function to model the data. This lesson will focus on functions that you are familiar with, linear and quadratic functions. We will also study a third type of function, which is the focus of our next unit of study, exponential functions. So let's take a look at these tables. So the first table I'm going to look at, I'll call this table one. Let me label that for you here so we know what we're talking about. Grab a pen. All right, so here's table one. All right, so the first thing I'm always looking to do when I'm using the strategies that I'm about to demonstrate is to see how the x values are changing, how our input values are changing. So if you look, our input values are increasing at a constant rate. And if we look, that's true in all of the other tables as well. So here in table one, table two, in table three, the input values are increasing at a constant rate. They're increasing at a rate of +1. Now, what I also want to do is I want to take a look at the output values. So if I look at table one or focus on table one, it looks like the first difference here is +6. So it looks like to get from the first input to the next input, we're adding 6. Same thing is true to get from the second to the third, third to the fourth, fourth to the fifth, and the fifth to the sixth input. So if you recognize a pattern like this in what we call the first differences in a data set, then the data that you're looking at is linear in nature. Now, what I've done is I've actually created a scatter plot of this data using Desmos so you can see that this actually follows a straight line. This data set follows a straight line. So we'll take a look here. So if you look on the left, you see the data table that we just generated. And on the right, we see that we do have a linear model. And if we wanted to write the equation for that would be y equals 6x plus 6, because if we go back to the data table, let me increase this size, sorry. Okay, if you look, um, as the inputs increase by 1, the outputs are increasing by 6, so that would give you a slope of 6 for that equation. And then when your input is 0, that's where your y-intercept is going to be. So your y-intercept would also be 6. So in this case, if the first differences are constant, then you're looking at data that is linear in nature. So a linear model would be appropriate equation or model to model that data. Let's look at table 2 and see if we can recognize a pattern in that data set. So in table 2, we already recognize that the x values, the input values, are increasing at a constant rate here. So they're increasing by 1. Let's take a look at the output values. So the output values here, it looks like that's plus 14. And then to get from the second to the third, it's plus 10. And then to get to the next one, it's plus 6, then plus 2. And then all of a sudden, it starts to decrease. It's actually minus 2. So clearly, this data table is not representing linear data. So let's take a look and see if there's any pattern in maybe the second differences. So let's take a look there. Okay, to get from 14 to 10, we're actually subtracting, we're going down 4 units. To get from 10 to 6, we're going down 4 units. 6 to 2, down 4 units. And then 2 to -2, down 4 units as well. So in this particular case, the first differences are not constant, but the second differences are. If that is the case, the data that you're looking at can be modeled with a quadratic function. So what I'm going to do right now is I'm going to go back to Desmos. And I've created a scatter plot here. Bear with me for a second. So let's turn off the linear scatter plot. And let's go down to the quadratic scatter plot. So here's the scatter plot. And what I'm going to do is I'm going to turn on the regression model. And there you can see that this data clearly looks quadratic in nature. It makes a parabolic graph. Okay, so if the second differences are constant, then the graph will be or the function will be quadratic in nature. Let's go back and take a look at table 3. All right, so if we try the first differences here, um, they're clearly not going to be constant. 1 to 3 is 2, and then 3 to 9 is increasing by 6. So again, you see that the first differences are not the same. And actually, if we went through, the second differences would not be the same either. So table 3 is not going to be linear in nature or quadratic in nature. So let's see if we can recognize another pattern. So grab a different color here. So it looks like to get from 1 to 3, we could either add 2 to 1 to get to 3, or we could multiply by 3. And then to get from 3 to 9, we can also multiply by 3. 9 to 27, we can multiply by 3. 27 to 81, multiply by 3 as well. And then 81 to 243, multiply by 3. So here it appears as x is increasing by a constant value. The outputs are increasing by a constant multiple. And if that's the case, the data that you're looking at is going to be exponential in nature. It's going to be modeled by an exponential curve. So let's go back to Desmos real quick. And we're going to turn off this quadratic. Sorry about that. Doesn't want to turn off. There we go. And now here's the data set that we had previously. And then here is the model. So you can see that this is an exponential curve. And you guys saw this back in Algebra 1, these exponential curves. Okay. Um, what we're going to do eventually is we're going to talk about how to write equations that model data or model situations that show either exponential growth or exponential decay. Right here, you're looking at an exponential growth model. Um, but again, soon in the next, maybe not the next video, but the video after that, the third video of this series, you'll see an exponential decay model as well. And I'll kind of talk about how those differ from each other, exponential growth and exponential decay models. All right, so let's kind of go back and summarize our findings. Make this larger here. So number 1 reads, can you identify the type of function, linear, quadratic, or exponential, that each table represents? How can we identify a linear function from its data? What about quadratic? What about exponential? So here's kind of the trick that you're going to use. So table 1 was linear in nature. And as we saw, as x changed by a constant amount, the first difference, which was either repeated addition or subtraction, in your output values is going to be constant. So again, if I kind of scroll back up to the table, in your first table, the one on the far left, so table 1, get that up a little bit more here. Okay. As x is increasing by 1, y is increasing by a constant amount. And that's going to be the case with linear values. It could also decrease by a constant amount as well. That would just mean that your line would have a negative slope. Table 2 was quadratic in nature. So as x changes by a constant amount, this should actually say the second difference. Sorry, let me change that right now. This should say the second difference is constant. So the second difference in y is going to be constant for a quadratic model. Now, quadratic models are typically going to involve, you'll hear something like, if this thing is falling, if an object is falling, or like if you throw a ball up in the air and it comes back down, or if you jump up in the air and you come back down. Okay, quadratic functions can be used to model that type of data. And then the last one, your exponential function. So as x changes by a constant amount, y changes by a constant multiple that's not equal to 1 or 0. So again, if we take a look at table 3, as x is increasing by 1, your output values are increasing by a constant multiple. Table 3 represents exponential growth. If this were exponential decay, um, your constant multiple that you would be working with would be somewhere between 0 and 1. And again, that's something that we'll cover in a later video as well. All right, so if you look to kind of just finish off these notes, there's a couple things I want to do. One, actually, part two here says to graph each function. I already did that on Desmos, so I'm not going to do that by hand here. If you want to see these graphs done out by hand, those are in my handwritten notes in Google Classroom. For number 3, says, does the graph help you see the trends more clearly? I would say yes, as long as your window is adjusted properly. Um, it tends to be a little bit easier just to see, okay, that's a linear model, that's a quadratic model, that's an exponential model by looking at the graph. But if you are given a table of data, looking at the first difference or the second difference to help you identify linear or quadratic patterns, very, very helpful. Or looking to see if your output values are changing by a constant multiple is really helpful, a really quick way to check and see if you're dealing with exponential data. So that's pretty much the content for this. What you guys are going to do next um, is you're going to complete, and I'm going to come back to this, you're going to complete problems 1, 2, and 3, and then also read the summary and how to use Desmos to create an exponential regression model. So that's what you're going to do, and that's what you're going to turn in as evidence of learning. I just want to give you a hint here. I just want to talk here quickly. For problem number 2, you're going to have to either work backwards or forwards by following a pattern to determine, or actually to, excuse me, to fill in the rest of these tables. So I'm going to kind of give you a hint on how to do that using table 1 and table 2 and also table 3. All right, so let's say that I kind of wanted to work this table, the first table, backwards to figure out what my output would be if I had an input of -1. Well, if you look, the first differences are telling me that I'm going up 6 every single time. So to figure out what this output would be, I'd have to figure out a number that when added to 6 is going to give me 6. So that number would have to be 0. And if I wanted to go back further, like one more, like let's say I wanted to know what the output would be for -2, then I'd have to go backwards and follow this pattern. That would be +6. So what number plus 6 is going to give me 0? That would be -6. Now for the quadratic patterns, it's a little bit trickier, but still, not that big of a deal. So here, if I work my way backwards, I'd have to go backwards 4 to find out the corresponding output for an input of -1. I'm sorry, so that would be a +18 for my first difference. And then what number plus 18 is going to give me 0? That would be -18. That's how you would work your way backwards on the second differences in a quadratic pattern. And then finally, the last one, again, if I wanted to find the output rather, that corresponded to an input of -1 in this table, what I'd have to do, again, is find a number that when multiplied times 3 gives me 1. That would be 1/3. Okay, so that should help you out answering problem number 2. All right, so there's going to be 2 more videos in this series. Those will be coming up soon. I hope that this was helpful. As always, if you have any questions or concerns, please feel free to email me or message me through Google Classroom. Thank you, and we will see you in the next one.